How's everyone doing today? Looks like we got audio, we got video. Everything is pretty solid. So, got a little bit of an update. The last stream we did was a little bit off topic from the disassembler that we've been working on, taking a look at the NAT slipstream attack that got released last week. We made a little bit of progress, but it was unfortunately kind of a bust. I think I'll revisit that in a little bit once I get more of a handle on ASN1 and some tooling around it. But in the meantime, we're going to jump back into the MSP430 disassembler. So if you were watching any of the previous episodes where we were working on it, you would know that we got decoding and parsing completely finished. We were able to do that as of the last session we were working on this. We had the decoding turning the machine code that we were parsing into some kind of intermediate representation that we had in memory that we could work on. I said I was going to do a bunch of refactoring and cleanup work and error handling and just like fixing things up to make it like a lot more pleasant to work with. That's all done, and we'll kind of walk through some of those changes shortly. The one big thing that's still missing is just documentation and getting the Rust doc set up. I'll probably do it off stream because it's not like the most interesting thing to work on. I assume that you all would agree with that. But yeah, so let's take a look at where we're at now. We can walk through those changes and get started on doing the actual printing. The printing is like the last big step in getting this disassembler to the point where we can start integrating it with Binary Ninja. And I kind of think this is like a 1 or 2 session kind of thing to get the printing done. I don't expect it to be like crazy long, and then the integration with Binary Ninja could be, pretty quick or long. I just don't know enough about it to really give like a real estimate yet. So I'm gonna switch back over to the desktop view so you can all see what I see on my screen, and we can start walking through some of the changes that have been in progress. So I think I mentioned already, I did some refactoring of the general structure. I got rid of that instruction module. Everything's pretty flat here now. It just didn't really make sense to me. Some general renaming, but mostly it's pretty similar to where it was before. We're taking in a byte slice and an address, and we're doing decoding of that. We're now using a real result type here rather than an option. And this is going to allow us to do error handling a little bit better. Before, I was just panicking everywhere, and while most of those cases were pretty exceptional cases, I wanted to, when something happened, I didn't want to take down the entire program. So now we're just doing general error handling. We have a result type that we're bringing in with us, and a decode error that provides some information about like where the error occurred and why. I think this will be a lot easier. A little bit of renaming around our operand handling. Addressing mode is gone, and we just have operand, and we have source and destination. And I think this simplifies it a little bit and makes it a little more clear like what's going on. The other big change I talked about before was some metaprogramming work. You'll remember before we had to go in and manually type out the types and methods for all of the different instruction types. That's all gone now for jumps and single and double operand instructions. I wrote some macros that will generate all these for us. You can see here, this is for the 2 operand one, the single operand one. There's 2 variants. And so we can just produce all these automatically at compile time. The only one that we're not doing that with is ret_i because it doesn't take any parameters. It is that special case one we saw. Instruction. You'll remember that this is that special case where it's PC or register 0, but like none of this is actually filled in. It didn't make sense. So I got rid of that special case, and we kind of moved it around a little bit. Basically, where is it? Here, we just check if it's that opcode, and if it is, then we return out early. Otherwise, we do our matching. So I think that covers the majority of like the big changes. All the code's up there, and you can go kind of check it out and see what's going on. But we're at a point where we have pretty good test coverage across the board, and I'm pretty confident at this point that the decoding and parsing is correct. And if we didn't do any more refactoring, we have test cases that are in a pretty good state where I'm not really concerned we won't be able to catch bugs if we introduce them. So how are we going to do the instruction printing? So I think I alluded to it a little bit in the past about the idea that I had. And this was one of the reasons I started doing a bunch of the refactoring and said I wanted to do some pieces first. I think the easiest way to do that is going to be to implement the display trait. So MSP Rust display. So display is a trait that comes with standard funct, and basically it implements the funct method. And if you are display, you get like a whole bunch of I think you get like string or something, which allows you to print something. So if you ever see some code like this, print line. If you ever see something like this, this general placeholder right here, it'll end up calling, I think it calls string on this, but maybe it calls funct. And that's what allows the format specifier to actually get printed. I'm trying to figure out like what the actual method is that we get from implementing this, but it ends up being like the magic trait that we need to kind of like get what we actually care about. So what I think we're going to end up doing is we're going to implement the display trait for basically every instruction type, and then on the instruction type itself, we'll implement display as well. And so what will end up happening is this will defer to the individual implementations, and then the individual implementations for each of these will, it'll have the logic in itself to figure out if it's representing an emulated instruction. So like one of these down here that has, based on the operands, has some semantic meaning, and it will figure out how to print itself based on that. And then it will defer to the, the source and the destination operands to print themselves. And that way we can just kind of defer all the way down. We don't really have to know much about, all the logic is pretty much like consolidated and encapsulated in the, correct places. So I'm going to go ahead and create a new branch here. Display instructions. It would help if I added the flag. So I think the easiest place to start is going to be the jump instructions. And the reason I'm saying that is because there are no there's no instructions that are emulated that ever use one of the jump instructions. So I think we're going to start here, and basically just for each one of these we're just going to impl it. So impl display for J and Z. And one of the things is like we did all these macros. We're not really going to be able to macro these because the actual logic is going to be tied up in here. So these we will have to actually do ourselves. And there may be a couple more traits that we end up implementing, and I'll kind of go over that probably in a future session. I have some ideas around building an assembler out of this as well, which would be kind of cool. We can bring that to Binary Ninja because it's one of the features they offer, and some helper traits that we might care about for Binary Ninja and other places we might end up using it itself. So basically, we just need to implement the funct method. You can see it takes a oh no, what did I do here? It takes a reference to self, and a mutable reference to funct formatter. It would help. So like I said, these are all pretty simple and straightforward to implement. So the first thing we're going to do is we're going to write the instruction. And I guess the question is, for these, maybe we can implement, we might be able to do this all with a macro for these ones. The other ones, probably not so much. Display for this is going into here. Mute. This is a funct formatter. So the only thing we're not going to get is the instruction for free, which is kind of unfortunate, but like we can always do it's like this will end up working, or we can just kind of do that. And then the offset, so we need to, let's get an example here. Is it examples or is let's see here. Just file. Yeah. RISC example. So a way to do this. think it's in SynFuzz. It'll have the code I actually care about. Yeah, so it's examples. All right. Let's get one of our tests out of here. MSP430 code. Okay. All right. Where it is? We forgot. So maybe we won't be able to do it this way. Let's go ahead and do this manually for now, and maybe we can do a refactor later that actually puts into the macro. And I think that's like pretty much, I don't need that. basically we're just going to go ahead and do this for all of them. And this will get us at least to the point where we can start testing whether or not this method will work. And I think that the move is going to end up being that we pass in a string here, and we just end up replacing that. So it ends up being like, ident and then Rust macro. Where's like the macro book? Maybe it's at the bottom. It's linked. Where are you? The little book of Rust macros. Syntax extensions. We don't care about that. Scoping. It might be in here. Basically, I'm looking for like this. This is the different captures that were allowed. And like a function, a struct, a module. So I think it'll end up being it might be an item or it might be an expression. It doesn't have to evaluate, so it might be able to be an item. So let's verify this works first, and then we can go and we can refactor the implementation there. This is JL. No method right fumped found for reference. We need, and we're gonna get a J. What is the first one we're doing here? It's JNZ. Is that not exported? forgot that. You know what? We can do this. Just identifier, and this is an item. Cannot find jump in this scope. Source. That's interesting. Use of undeclared type JNZ. I wonder if it has to be an expression then. Undeclared crate or module, MSP430. Use this. I thought that was gone with RISC 2018. That shouldn't be required. Oh. Format must be a string literal. Okay, so it is printing. That's good. It's not doing the substitution, which is our problem. Rust macro substitute in string. I mean, we could always... We could always do this. That works. The one thing I do want to see is kind of like how they do their printing in here. Give me 1 second to log in and not do this on stream. All right. Sure, this is fine. So let's look at some jump instructions. So we have J0, and it's so the one thing I don't okay, so that alternate form of printing should be used. The alternate forms are is that and it is after the okay, so then yeah, it should just be like this basically. This is how to get the correct values. And so presumably if we were to go get a negative number now, like this for instance, this should give us the negative value. Oh, that's interesting. I don't want it. That is so what is the format specifier. Got width, we got fill and alignment, sign. Alternate form of printing should be used. The alternate forms are So we want to find negative hex. So it looks like we need to make our own formatter for it. So assign primitive number to its hexadecimal representation in a way that preserves the number sign. It turns out the current position, lower hex, and relatives for signed primitive integers is unsigned, regardless of what the extra formatting flags that I did add. These implementations appear simply reinterpret the number as an unsigned counterpart for formatting purposes. So that's unfortunate. There's a hacky solution that we can do, which is we can turn this back into a positive number, and depending on the current sign, like we could do this. It's less than 0. Basically, we can do this, but this seems like pretty hacky, and I don't really like it. It's also not very efficient. Is that what we're supposed to be doing? Kinetic 6? Yeah. So, like that works. I just don't like it, because it's kind of gross and hacky. But what's the trait called? Lower What did we get for -1? We'll do it -6. It would help if we Is this the stack overflow question we saw earlier? Yeah. Is it not printing? Why won't you print? Paste. So this implementation works. We get our jumps properly. The one thing we probably do want to verify is that the naming here is what the real one uses. The other thing we don't have control over is how much space there is in between the opcode and the operand, and the instruction and the operand. I don't know if we're gonna want that to be configurable. Like right here, like this is, I don't know, like some amount, but the I don't know what binary ninja is gonna want when we get to that point, and so you might want to make that configurable in some way or something. But I'm just looking at the instructions right now to see like what they use. So we see like JNZ, JZ. I don't see a lot of other like jump instructions. Regular jump, which is what we expect. JL is used, JEQ. So which one is JEQ? Because we're probably going to want to end up changing that to be whatever. So JEQ. And the reason like these are different is that some of these have two meanings. So like JEQ is the same as JZ. And so I'm not sure like why you would choose one or the other. Like in this case, we see both being used. Where's JEQ? Like JEQ being used right here. Maybe because it has a compare above it. Like if we were to look for like a JZ, like where's JNZ? I thought we saw a JZ earlier too. Yeah, so like maybe it cares about like what's in front of it. Like if it's a test, then it uses JZ, and if it's not, then it uses an equal or something like that. I don't know if that makes sense because it's not like I don't want to build a contextually aware formatter, but like maybe that is a good thing to have in this case. So I don't know. This seems to work, and like the approach seems like pretty reasonable. And so we can implement display for this. So I think this will fail to compile because, oh, yeah, that needs to be a mute. I don't think this will work because all of these don't implement display. It looks like it does though. So if we went back to here and we got rid of that, like could we just do why did it overflow the stack? I think we have to do that. Do we not need to implement this? So instruction doesn't implement it, which we understand. I mean, that's correct. Enum self Can you deref? Is it just dereferencing it? No. Like what I think is happening is this is calling it on itself rather than deferring it to the individual implementation here. Ref is gone. So this is what we thought was happening. It doesn't give us what we're looking for though, which is the actual issue. Is so like the way we solve this is we do a big match statement here, and we implement it for all of these. There should be an easier way to do this. Something that like doesn't require like actually doing this. why is that returning? We might have to do... Yeah, so maybe it is implementation we end up going with, is just doing that. It's not like this is going to ever change. Like, the instruction set is fixed. It's just unfortunate that we have to, do this. Expected tuple struct or struct variant and found hand. Oh, this needs to be instruction. Format argument must be a oh, god damn it, I forgot. Yeah, okay, perfect. So we're gonna have to go and all right, let's do this. All right, so that's partially fixed. For these, we're gonna do write f. And that's because we've already done the implementation of display for jumps. rest of these, we're going to go and do unimplemented. And so this will end up panicking as we call it, but none of our tests or anything call this right now. So I think we're okay. All right, it's pretty solid. Not what I was hoping for, but you know, it'll work. This is, yeah, that's fine, because we're going to go back and fix all these later. I don't care enough. Source operand. It's telling me I don't need super. I don't know why it doesn't like that. Like it 100% needs that there. Oh, I guess it doesn't. Oh, it does. Okay. All right. So the next thing we're going to do is go do it for all of the single operand instructions. We're going to have to go implement these. So the question we have is whether any of these emulated instructions are single operand. Because if they're not, then the single operand ones we can do the same way with the macro. It looks like add C is there, move bic dad sub bic bis add zor compare bis. So yeah, so yes, I think the move is for these single operand ones as well. We can do all of these with the same method of using the macro. And let's see here. Single operand. We have two different ones here that we're gonna have to do, plus a special case for ret_i. So let's do the ret_i one first. Front display for ret_i. Unresolved reference. Oh, I gotta do standard funct. All right. So ret_i is implemented. We're gonna do. Where's instruction? And single operand. We're done with that. So for these, we're going to impl front display for E. Did I just do I before, or what did I do for these? I did N for name. All right, so we are going to do N, and then self source. So this should be fine. The only thing we're going to have to do is we're going to have to go to source now and implement display for source. We should be able to literally copy and paste this here. And we'll even be able to do this somewhat for, like there probably are some of these that aren't used. Well, maybe not. I don't know. I don't know if every single one of these supports emulated instructions. If they don't, we could build like a macro that does like a non-emulated version that does this stuff. But you know, it's fine. So we're done there. That's fully implemented. We need to go to operand now, and we have to implement display for source, and we will have to do it for destination as well. The standard font. And so what we're going to do here is we're going to do another match statement for all of these, and basically whatever we see based on this, we're going to end up, you know, printing properly. Self. So, R oh man, this is even worse. So based on S, if it's, well, can register direct. Let's go to AS real quick. So like we should be able to get a register direct for anything that's R2, R3, R0, but we can get the stack pointer, which which one is the stack pointer? Is that 4? What is this? 0, so it's 1 is SP. Indexed and register and index. That SP. Yeah, it'll be exhaustive, don't worry. Can indexed be anything that's not a stack pointer or it cannot? Okay. Register indirect. And that is going to be our register indirect auto increment. It's basically just this. We had that a plus at the end. And so this covers that. Yeah, okay. Symbolic. Symbolic So this is going to be it's an I-16. Yeah. Symbolic, immediate. So this ends up being that. PC. Wait, that can't be right. The operand is the next word in the instructions. Okay, so this should be an I-16. It's the memory and address PC. I mean, I think this means that it's just this. It's a, oh yeah, immediate. It is, okay. What do I think of Rust and Go in 2021? So I think they solve different problems. I use both pretty heavily, depending on what I'm doing. Go is great if you just need to like write some quick code. If you're building like tooling, it's nice to like really get like a web service or any kind of like service. Networked code. I think there's a lot of limitations in the language. Like the lack of generics is really frustrating. It's something that's bothered me for a long time. It has a really good standard library, but there's I don't know. Like they've chosen to ignore certain parts to get them like a lot further faster, and as long as you don't ever need to use those specific things, like it's great. Like you can do those things, and it's fine. But as soon as you need to, like everything kind of just falls apart. I think the developers are kind of not great sometimes. They're like fighting against like package management for so long, and a handful of other issues. But I don't know. I use them both, and I think they both have their places. I chose Rust here because I wanted something that I can embed easily into a shared object that I can bring into other stuff. Compile time safety, and there's no like green thread kind of runtime with Go routines that has to get managed. So it's like safer to bring into other stuff. Like you could build a shared object in Go, but it's pretty heavyweight, and so it doesn't really seem like it's a good option for like this use case. So this is an offset, it seems like, which if you don't know PC, you won't know what that is. For now, it seems fine. Like we can use that implementation, and we'll deal with it later as we get to that point. Absolute. So this is an address. Where is absolute? Absolute, okay. This is a Keychron K2. It's okay. It's got cherry browns in it. Hold it up if I can do it. It's fine. Like it's nothing special, and like there's some things I don't like about it. For whatever reason, it's a USB, but for whatever reason, when I boot up, my BIOS doesn't ever see it. And it's not an issue with the USB in the BIOS because if I plug in other USB keyboards, it like they show up. So I'm not sure exactly why this one specifically doesn't show up as a keyboard, but I basically have to pull out like another keyboard to like go interact with the BIOS, which is kind of irritating. So this is fine. This is gonna be an address, whereas this is a specific value. I guess maybe we do hex for it. I don't know. That seems like it's not a bad idea. And then constant. And this for sure is going to be hex. So the thing that we don't get here is this. We're going to have to add in like this logic, which I don't like. Okay, I wonder if we can overload that. It's unfortunate. So that's implemented now. I guess we might as well do this one while we're here as well. Font display for destination. Match self destination register direct. What was the register direct implementation? It's this. Literally just copy this. But for AD, it can be any of them. So actually, let's... Zero, 1, 2, 3, R, let's see. So 0, 1, 2, 3. Stack pointer. SR. So I'm not sure if you can actually do CG, but you know, I guess that's probably correct. Indexed. R, I, and probably the same thing. We're gonna have to add in this annoying logic for the plus and minus. All right, so it's we don't do, so for indexed, yeah, okay. So for index, it's going to be PC or IA 1. PC, that's SP. Why is that? SP R C G. So we're still gonna have to go in and we're gonna have to do the fix for the negatives. We're gonna probably want to find a better solution long term. But at this point, we can at least go back into here and we can if we were going to go to, I don't know, like what's a single instruction one we can do? Yeah. No implementation for U8 equals integer. It's an operand. Okay. Can I do that? No, I can't. Cannot find these. Failed to resolve. Single operand. I fucked something up here. I forgot to do these. Cannot find push in this scope. No rules. Did I not? I didn't update this. Missing tokens. Okay. So we're not getting our negative values, which is expected. It's a weird instruction, but like, I guess we could go see this assembles the same way. Yeah, leave it. Assemble. So we got 1910 FCFF, and that's expected because of the ones complement. We can go in and we can fix all of these. We basically need to go and grab this. Single operand. We want this itself, which is unfortunate. This is the negative. Maybe this is something we want to fix first, like globally. lower hex. Yeah, that's unfortunate. So we might be able to add our own formatter that basically does what we're doing, which is it gets the absolute value. Custom formatter. Negative hex. There was an example, I think in here. A new type in order to provide a distinct implementation of so that's the issue, is we would have give me lower hex. that is expected. Oh. So for all of these, we're going to do that same logic, which is super frustrating. This will always be a positive number, which is fine. Immediate. This can be a negative value. Same as this. Yeah, okay, so that's correct. And then for this, we're going to have to do all that logic in here as well. I've hit that button so many times by accident. So this should get us printing to, basically all the right values that we actually care about here. Still not sure why that's being warned about, but sure. We're still getting these. Yeah, we still are getting those. I don't understand. We're gonna go back and just use the super. It is what it is. We can add that in there later. So we're getting the right printing here. The thing that we're not getting yet is we're not getting our. We haven't done any of these yet. And this is where all the hard stuff comes in. So let's do something real quick. So we have move, add C, sub C, sub compare, dad, bit, bic, bis, zorn, and let's see if there's any of these that are not used to implement emulated instruction. So add C is being used, move is being used, bic is being used, dad is being used, sub is being used, bic, bis, add, zorn, move, add C, sub C, bis, compare. So basically bit and bit and are the only ones that we could get a default implementation. Cool. Hey, doing pretty well. All the decoding and the parsing is done. We got an internal representation of all the instructions, working on printing stuff right now. And basically once the printing is all done for everything that's not one of these instructions. So once that's done, I'm hoping today we'll be done with all the printing, as well as the emulated instructions, and then the next session we can start wiring it up into Binary Ninja and seeing if it works and what the performance is like, and if it actually does things correctly. I actually need to go and look at the API and figure out one of the things I'm not sure about. So we're doing all the writing of the instructions out, and yeah, definitely. I up until this point, it's pretty much just been looking at it in the debugger and verifying the tests are correct. The one thing I'm unsure about is for the textual data that we give back to Binary Ninja. Does it care what kind of spacing we have in between instructions and operands or any of that? Does it take in any specific formatting, or does it care what it is? or is there like a structure that we have to populate it? I think the what was like there's the API in here. It's architecture. We have to implement instruction text, I think. You send different components separated by tokens. Okay. So basically we're going to want to tokenize... when we do this implementation, we're probably going to want to turn all of the individual instructions into here into tokens and then pass those forward. You get a disassembly line in the API, you can see the different token types. Well, let's see if we can do that. Do I have the file here? Where's the Python window? There's like a thing for that. Python console. So from here, I should be able to do, what is this? It's like binary view. How do I get my current location? Instruction text token type. Okay. And so it just comes down to how good, like, or how well, like, we tokenize and pass to Binary Ninja. That makes sense. And so for things like denoting that something is a an address or something, like, do we need is that part of like the token that we pass? Like, we just like, yeah, like this number right here, this is actually an address. This isn't just like an immediate value. I mean, if that's the case, maybe it doesn't even make sense to spend all this time building out textual based output, because like we're not actually going to use any of this. We're going to translate all of our instructions into whatever the tokens are that Binary Ninja expects, and that's fine because that's easy. That's actually much easier than what we're doing here, I think. Yeah. So, for if we wanted to say like a number is like referencing an address in the in the file somewhere, like there's like a number like hex 5A. If we want to denote that that's like a reference to the actual memory and not like the immediate value, that's just like something we describe as the token. Like there's a token for like an immediate value versus like an address. I wish I had an easy way to get the stuff from this computer onto this one so I can pull it up on the computer. Okay, cool. Perfect. So yeah, one of the really, really frustrating parts about this is that the way that that Rust handles like displaying its numbers as hex, it'll only display negative hex values as two's complement values. So I have to do all this like really crazy checks and like gross things here to like, if the number is 0, I have to like, or 0 or greater, I have to, I can print it. But if it's less, then I have to like do an absolute value of it and then prefix the negative. So that seems much easier. So maybe it's not even worth doing like all this printing, because I'm never gonna like actually care about the ability to display this stuff. I mean, I guess I might as well just finish it out. But I think that if that's the case, probably need to still implement whatever the logic is for like emulated instructions, so that those get I can translate those easily when I build the token stream. And so I'm guessing that I'll probably just do an impl. I'll build a trait for something that's like an into impl stream or something like that, and we can just do it that way. That seems like the simplest solution. Cool. Well, that actually makes everything much easier. I need to go read the docs and actually figure out like what this ends up looking like, but I think it's significantly easier to do that than it is to do the printing. I don't know why there's errors here. Okay. Let's go back here, make sure all the tests pass still. That looks good. Yeah, I'm gonna do it off stream. I think probably I'll read that before the next one, but I think at the next stream we're basically ready to go. And we'll get things integrated. We'll see what it takes to actually do this. Cool. Yeah. Have a good night. Enjoy dinner. So lifting's ready. So cool. Yeah. So as soon as I can do the disassembly part first, and then we can do lifting later. Lifting's important, but I think it'll work without it. Awesome. Have a good night. So let's go ahead and I guess let's implement the let's implement display for all of these, and then we'll get printing done. Need standard font. Mute font formatter. Right. F. Move. Self. Source. Destination. The only other thing that we need to do is if self operand width is 1, That's the only difference, is it's moving the bytes. That's pretty much it. Which ones? Oh, yeah, these all have the operand width. It's yeah. This. If self operand width is 1, there. That's it. So we're going to do all these default ones here. And basically the default ones are just going to get us to the point where we can, we don't have to worry about any of the emulated ones yet. And then we'll go and we can start adding in the logic for the emulated ones. Almost done. So and then the last one is and. Let's go ahead into here and we'll add these. good. So let's see if we can find one of the two operand instructions. We'll put it in there and we'll decode it and see what it gives us. I mean, I don't know, like Santa Cruz is probably fine. Let's see what we can find here. So let data equal, it's 9 4F 6A 47 00 24. That looks pretty good. We're getting decoding working. So the only thing we don't have is we don't have emulated yet, and we can go and we can start working on that right now. Yeah, we're about 2 hours in. Let me get some lights on in here. Like, realistically, I don't think the emulated will be that complicated, because they're pretty specific. They're pretty specific cases. So go to 2 operand. We don't need a single operand anymore. I mean, we're gonna have to get some tests in here probably, or some just sample stuff done. But one sec. So the first one we're going to do is ADC. So if we go to add C, in here, we're just going to go ahead and yeah, so it does support can we do that? Yeah, all right. I think we're in a little bit of refactoring here. Does Rust have a Rust, not trinary, what is the kind of statement? It's a ternary statement. Yeah. So this is the shitty part, is that we're going to have to build this into each one of these branches. If self bandwidth 0, we do byte suffix so of course we have to fix all these now. And we'll go fix these for the ones that are all using the macros. That'll be much quicker. And all right. So these are single operand, and for with the width, we're gonna go in and just do this. All right. Instruction, we'll move those into there. So it's those need to be public. So if I don't do pub there, can I access it via unknown field? Single operand. This is wrong. It should be name, suffix, source. Create instruction byte, okay. So that's single, and then this is double. Everything still passes, cool, all right. So that's perfect. So we need to go back to here, ADC. All right, so if source equals so that is, now is it, like, could you do this as, is it a constant or is it a, I guess it would be a constant. from the destination. So add carry. So what is ADC? Say we did assembler. ADC R15. So it's encoded as 0F63. That is so 6P0 110 0011 0000 1, 2, 3, 4. Okay, so that's register 15. AS is 0. Source ends up being 3. So that's the constant generator. Yeah, so constant generator. Source. So basically, if it's that, what's the easiest way to do this? Like, do I want to just, could you let int equal add C? We could do int equals ADC now. Or if add, so does it just mean if it's like, if I do RLC R15, where is that? RLC, that just means the source and the destination are, so is it 6F, 0F, so it's, yeah, okay. Destination self source equals self destination int equals RLC. Okay, so we did the add C ones. So move if so just if source is PC, or if the destination is PC. Right. And so we want to make sure we don't do this, because BR you can't do a there's no suffix for it. So what other moves are there? Better to just do returns. All right. So the next move is constant 0 into R3. If source destination equals destination register direct 3. Then it's a NOP. Pop. Source. Is register indirect auto increment, and it's the stack pointer is what? What register are we? It's 1? I kind of think it's 1. Yeah. Yeah, it's 1. So the source is an auto increment 1, and self destination is oh no, we're good. It's just if it's that. This is pop. Interesting, and we don't get the suffix on this. And the destination is PC. Zero. That's a pop. That's a ret. You know what? I think we can do this a little bit cleaner. Then we do a ret. Pop. Right? Yeah. What did I just do? No. Okay. These are our moves. So we got some Bics. All right. A lot of them are Bic. So if self source, so that's if destination equals destination register direct, SR is 2. All right, if self source source register direct, no, constant. Constant 1, 4, and 2. CLRC. And G. All right. Bic. Constant 8. D int. Oh yeah, no, that's fine because we're not we ignore where the register is for that. We just know it's a constant, which is great. That's a bic. All right, we have DADD. And so that's if the constant is 0. The other dance. Yeah, okay. Self, is it destination? No, source. C. Dad C. Oh. What was the other one where our BR is wrong still as a destination? Yeah. ADC. Yeah. RLC. ADC. ADC can do a suffix. RLC can do a suffix. Can. That looks correct. So DADD. DADC has a suffix, and it removes the source. Okay. And sub. So the interesting thing about these is that when we start building our token stream, we're probably going to have to refactor this logic out into something that can generate that token stream as well. Because, I mean, this will effectively be the same thing. Like, maybe for display, we'll generate a token stream, and then we'll turn that token stream into well, no, because the token stream won't be part of this. It'll be part of the Binary Ninja implementation and not this. So we might have to copy this, which is unfortunate, but I'm not sure yet. So this is sub. If self source equals source constant 0 or 1, we're gonna deck deck D else yeah, so we could do that. Do match self source constant 1 I guess it's not like necessarily any more clear. stick. I think this is what we haven't done yet. This. So if it's 8, it's eint. If it's 4, it's set n. If it's 2, it's set z. Set c. Otherwise, it is bis. So we gotta do add. Oh, we just did the deck ones, didn't we? Or sub ones. Yeah. Yeah, here, this logic. It's basically the same thing. If it's 1, it's inc. D. We've got Zor. There's only one for Zor. If self source constant -1, then it's inv. Okay, we've done the moves, we've done the adds, we've done the add C's. We haven't done sub C yet. Self source SBC and then test, which is a compare. If self source equals 0, TST Was it 102? Oh no, we can't compare them. Damn. RLC. Yeah, there's a few of them. It's RLC and RRC, I think. RLC, RLA. So was it 102? Oh, it is only one. So add C for RLC. Damn. So how do we do RLA then? Add C. RLA and RLC. So one is add and one is add C. I just never implemented it. That's why. Self source. And this ends up being RLA. Damn. So there's gonna be two of these that we're not able to do. All right. If so It's RLA is for add. Inc. These don't have it. RLA and add does support it, okay. Deck. Where's Dad's C? Okay. It's RLA and RLC, basically they're the problem. Compare two types. We define partial equality for comparing with any type. Oh, all right. So yeah, that's what we need to do. Operand. So source and goal standard compare partial EQ destination So basically, we just have to make sure that both are not equal constant or self how do I get iflets here? Yeah, so that's what we want is self interesting. They're not constants. Oh, this is gonna be much more complicated. Check if... Well... I guess not really. If register direct then if let source register direct the self dest r equals source r else if let destination indexed dest r dest I, that's other, dest I equals source I. So I think that's it. I think we can now compare. We can compare these. That's pretty cool. All right. So we just implemented RLA. Like, let's see if we can do that. So RLA R15. Okay. So damn it. New directory. Yep, do that. Rust file. Run. So we said it was 0f, 5f. MSP430 disk, decode, data 0. That's kind of correct. So RLA. RLA, RLC. Zero F, 6F. Yeah, cool. It's working. I don't know what I just did here, but that's bad. There. All right. Let's just go make sure that all these are correct for what they're printing. that looks right. Set C, set Z, set N. Yeah, that's right. Clear C, clear N, clear Z, dint. Dead C is destination. Test is correct. Deck D. RLC. Yep. RLA. Inc D. Those look good. Pop. Ret. Nop. BR. Yeah. We got it. You know what? Let's actually get rid of this. We don't need this anymore. Let's make sure the tests pass, which they do. All right. Complete printing of instructions. We'll just do reword. Printing. Allow all instructions to be printed. This includes special cases. Instructions. Due to the way lower hex is implemented, non-ideal values visited the future. All right. Cool. I'm going to call it for the night. We got done everything we wanted to do today. We now have instruction printing. Like I said, this becomes a lot less important now that we know that we need to basically create a token stream for the Binary Ninja implementation. But as we're doing that token stream, all of the logic for producing those tokens is going to be like more or less the same as the logic we have here. So we're going to be able to end up using this regardless, and this is nice to have just because it's something you might want to be able to do. This crate is like pretty much ready to go. I think I'm going to make one change still, which is rename this to MSP430 ASM rather than dis, because I think we're going to end up turning this into an assembler as well. That'll be something we do after we get it integrated with Binary Ninja. But like I said earlier, like it's functionality that Binary Ninja provides for, you know, all of the produced like the plugins that come with it. So I think once we get this integrated, we get the lifting working, or maybe if the lifting is not trivial to do because it's not implemented yet in Rust, after we get it integrated, but before the lifting, we'll go back and we'll build, you know, the assembly portion. We're going to end up doing it in two parts. One is basically turning one of these instructions into the encoded machine code, and that's going to be pretty straightforward. It's going to be really simple to do, I think. Effectively the same as what we did today, only all these special cases don't have to get implemented because we have the underlying instruction. So that makes it a little bit easier. The harder piece that's actually going to be a little more difficult is going to be building the assembler front end, which basically can read in like assembly text and then convert it into the internal representation of these instructions. And that's going to be probably a bit more work, but we'll see how that goes. Getting the assembly portion working first will be pretty trivial, I think, and is a short session probably. But yeah, hope you all enjoyed it. Hope you all learned something. We'll be back probably sometime this week to take a look at the binary ninja stuff, or maybe we'll jump back into microcorruption and finish up the last 2 levels, or if I can figure out the ASN1 stuff, jump back into the NAT slipstreaming side of things. But I'll see you all next time. Bye.